Last time we talked about Taylor expansions, and in particular, a special case of Taylor expansions, which were the Maclaurin expansions. Remember, the Maclaurin expansions or the Taylor expansions about A equals 0. So they look like this. F upper n evaluated at 0 times x to the n over n factorial. This video looks at specific functions and how one determines the Maclaurin expansion form. All right, so the first function we're going to look at, relatively easy one, f of x equals e to the x. All right, so here's the Maclaurin expansion. We need to figure out what f upper n at any 0 is, what its value is, and that's what we're going to stick in there. Well, but you know that if you take e to the x and you take any derivative of e to the x, what do you get back? E to the x, right? So f upper n of x is always e to the x. Okay, now I'm going to plug in 0 here. Well, then f upper n, plug in 0, is just e to the 0, which of course is 1. And this is true for any n. So everywhere I see an f upper n of 0, I just stick in 1. What does that give me? This expansion right here. The summation n running from 0 to infinity of x to the n over n factorial. That is the Maclaurin expansion for e to the x. And over here on this side, I've just written a few terms so that you get a sense of what it is. What is it? 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and you just keep going. All right, our second example is going to be the Maclaurin expansion for one of the hyperbolic functions, sinh x. All right, so let's think about that. And again, this is the Maclaurin expansion, so all I need to do is figure out what f upper n at any 0 is. Well, it shouldn't be hard to figure out what f upper 0 is sinh. F upper 1 is cosh. F upper 2 is back to sinh. F upper 3 is cosh. Get it? So it alternates. And the point is, f upper n of x is sinh x when n is even. And therefore, f upper n at 0 is just sinh of 0 when n is even. But what's sinh of 0? And the answer is it's just 0. Now, when n is odd, f upper n of x is cosh, right? Because it just alternates between cosh and sinh. So f upper n at 0, when n is odd, is just cosh 0, and cosh 0 is just 1. All right, so what does that do to the series? Well, the answer is anytime n is even, I get a value of 0. Anytime n is odd, I get a value of 1. So in this expansion, the only powers that are left are the odd powers. All the even powers go away because this constant is 0. All right, so how can I write that? Sinh of x then is n running from 0 to infinity of, okay, if I want to skip every other one, if I only want to write the odd ones, I can do it like this, 2n plus 1, right? So when n is 0, I get 1. When n is 1, I get 3. When n is 2, I get 5. You get it? Now, all the even ones go away because sinh 0 is 0. All right, and the odd ones, f upper n just has a value of 1. Okay, so that's why I just have x to a certain power. All right, so what is sinh x? It turns out to be the Maclaurin expansion for the hyperbolic sine is n running from 0 to infinity of x to the 2n plus 1 over 2n plus 1 factorial. And now what have I done? I've just written out a few terms. All right, x plus x cubed over 3 factorial plus x to the 5th over 5 factorial plus dot, dot, dot. All right. If I look at another example of the Maclaurin expansion, I'm going to look at the example f of x equal to the hyperbolic cosine. Well, there, right, it's in some sense just opposite of this. F upper n of x is just cosh when n is even, right? And whenever n's odd, f upper n of x is just sinh. But when I plug in 0 for cosh, just like above, I get 1. When I plug in 0 for sinh, I get 0. But now what does it mean? All the odd powers go away because they're coefficient 0. And the even powers are the only ones that are picked out. And in which case, f upper n has a value of 1. All right, so how can I write that? Cosh x turns out to be the summation n running from 0 to infinity of x sub 2n. 2n allows me to write only the even powers over what 2n factorial, and I can run n from 0 to infinity again. All right, so cosh turns out to be what? 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial plus x to the 6th over 6 factorial plus x to the 8th over 8 factorial plus dot, dot, dot. Get it? All right. Now, and I can do that with all of my common functions. So what do I get? Well, I get what I call the common Maclaurin series expansions. And you really should know these. And in fact, if I were giving an exam on campus, I would require you to know these. You ought to know them regardless. And of course, now I can't really require it because when I test, I'm not going to be around. All right, so e to the x, that was this. Cosh x, we found to be this. Sinh x, we found to be this. Now, when you start looking at cosine and sine, what happens is this. You get an alternating sign signature, right? Why? Well, because for the hyperbolics, of course, the derivative of sinh is cosh and the derivative of cosh is sinh. But for the trig functions, the derivative of sine is cosine, and the derivative of cosine is what? Minus sine, and the derivative of minus sine is minus cosine. So, one even power will have cosine, the other one will have minus cosine. You get it? 1 plus, 1 minus. So the only difference between the hyperbolic cosine and the cosine is that alternating change in sign. By the same token, the only difference between the hyperbolic sine and the sine is that alternating plus minus, which we find in sine. Now, let me try to show you how you would expect cosh to only have even powers. Well, think about the function hyperbolic cosine. The hyperbolic cosine, just like the cosine, is an even function. An even function means what? It's symmetric with respect to the y-axis. Well, if they're even functions, don't you think it would be common sense that they only have even powers of x? And sure enough, they only have even powers of x. But what about the hyperbolic sine and the sine? Well, the hyperbolic sine function, sinh, is an odd function. Yes, it is. Which means it's symmetric with respect to the origin, right? Well, wouldn't you expect an odd function to have an expansion that only has odd powers of x? I would. And so sinh is an odd function, has only odd powers of x. Sine is also an odd function, only has odd powers of x. And by the way, additionally, what? Sinh of 0 is 0? Lo and behold, when I plug in 0 over here, since everything has an x, it goes away. By the way, cosh of 0, on the other hand, is what? 1. And lo and behold, when I plug in 0 for x up here, everything goes away except what? 1. So there are some reasons that I would like to argue that these expansions, if you think about the properties of the function, are common sense. It just depends on how common your sense is. The last, and by the way, when we talked about power series, we saw for the interval of convergence, right? What x's do these functions converge at? And we determined interval of convergence by using the ratio test. All of these functions right here have an interval of convergence of minus infinity to infinity. So, and you could run that yourself by the ratio test. In other words, they converge everywhere. Absolutely everywhere. And now the very last common Maclaurin series expansion I'm going to get is 1 over 1 minus x. Those derivatives are a little more complicated to compute, but I claim that when you do that, you get the expansion. 1 over 1 minus x is what? 1 plus x squared plus x cubed, the summation in running from 0 to infinity of x to the n. What is that? Well, like we've seen before, that, my friends, that is a geometric series. It's a geometric series where a is 0, and my ratio r is just x. Okay, and if you go back to our formula for geometric series, it is what? A over 1 minus r. And I just told you, a is 1 and r is x. So in fact, 1 over 1 minus x is a geometric series, and it looks like a geometric series. And there you have it. That's all I want to talk about today. Next time, I'm going to show you how to develop some less common series.